All right, welcome back. Today, we are tackling a massive question, maybe one of the biggest in all of tech right now. How in the world do you build and train these colossal AI models that are literally changing everything? I mean, we're talking about a scale that, honestly, felt like pure science fiction just a handful of years ago. So, yeah, let's just cut right to the chase. How do you train an AI that has, well, it's not a million parameters, it's not even a billion, we're talking about over a trillion. And if you think of these parameters as kind of like the individual synapses in a brain, you start to realize that getting them all to work together in harmony, well, that's just a monumental, mind-boggling feat of engineering. Just look at that number for a second. That's $1.75 trillion. To put that into perspective, I mean, trying to even wrap your head around that is like trying to count every single grain of sand on a massive beach. It's not just a big number, you know? It represents a genuine, fundamental wall you hit in computing. Okay, so if you're an engineer trying to train a model this big, you're basically facing down three major villains. First up, you run out of memory on your chips. Like, almost instantly. Poof, gone. Second, just getting all the different computer chips to talk to each other becomes this huge, crippling bottleneck. And third, the whole training process is so long and so complex that things can just fail catastrophically, and that can wipe out weeks, even months of work in an instant. So how do we fight back against these villains? Well, here's our game plan for today. We're going to start by digging into the challenge itself. Then we'll introduce the playbook that's designed to solve it. We'll get into the weeds of parallelism, figure out how to win the memory game, and finally, we'll see how a framework called Nanotron pulls it all together. All right, let's kick things off. Section 1, the Ultra-Scale Challenge. And really, this is all about understanding the sheer Herculean effort it takes to build one of these computational mountains. Okay, moving on to Section 2, introducing the playbook. You know, any great challenge needs a guide, right? A set of strategies to get you through the tough spots. And for this massive task, the AI community has developed what you can think of as the Ultra-Scale Playbook, and frameworks like Nanotron are really leading the charge. And I want you to think of this playbook less like some boring, dry technical manual and more like an essential toolkit. It's the map and compass for any engineer or researcher who's brave enough to venture into this wild, treacherous landscape of training these giant models. It basically shows you the proven paths so you can avoid all those nasty pitfalls we just talked about. And that brings us to Section 3, mastering parallelism. This is really the first and maybe the most important strategy in the whole playbook. I mean, if one computer isn't powerful enough, the obvious answer is use a ton of them, right? But it's not that simple. How you split up the work is absolutely crucial. It really is like conducting an orchestra. You can't just tell everyone to play louder. You got to give each section a very specific part to play so it all comes together in harmony. So the most straightforward way to do this is something called data parallelism. Picture it this way. You have 10 identical factories. You give each factory the exact same blueprint, that's the AI model, but you give each one a different pile of raw materials to work on. So here, every single GPU gets a full copy of the AI, but it just chews on a different chunk of the training data. It's simple, and it works. For a while. But then things get a lot more sophisticated with what's called tensor parallelism. Now, instead of just splitting up the data, we're actually splitting up the AI's thought process itself. You're taking a single complex math problem from inside one layer of the model and breaking it into pieces for multiple GPUs to solve together. This became absolutely essential when the layers themselves just got too big to fit on one chip. And there's a third way, pipeline parallelism. This one's easy to picture. Think of a factory assembly line for a car. The AI model's layers are basically chained together in a sequence. So the first GPU works on layer 1, then it passes its result to the second GPU, which handles layer 2, and on down the line. This was the answer to models becoming incredibly deep. We're talking hundreds and hundreds of layers. So what's the takeaway here? Well, as you can probably guess, there's no single magic bullet. Each of these strategies has its own trade-offs. Data parallelism is pretty simple, but it creates a ton of network traffic to keep all the models in sync. Tensor parallelism, even more communication, but you just can't live without it for those massive layers. And pipeline parallelism is great for saving memory, but you risk having some of your expensive GPUs just sitting around waiting their turn. The real genius, the real art, is in combining them. You use pipeline parallelism between groups of GPUs, and then within each of those groups, you use tensor parallelism. That's how you get the best of all worlds. Okay, on to Section 4. winning the memory game. Because even with all these clever ways to split up the work, you slam headfirst into another problem: the physical memory on each and every GPU. See, an AI model isn't just storing its own parameters. While it's training, it creates these huge temporary files called activations. The best way to think of it is like scratch paper. It's the space the model uses for its rough calculations, and it takes up a ton of room, but it's absolutely essential for the model to learn anything. And this quote just says it all, doesn't it? Memory is not a suggestion, it's a hard wall. That is the brutal reality for engineers. You can't negotiate with it, you can't ask it to be a little more flexible. It is a hard physical limit. If your model and all that scratch paper data don't fit, the whole thing just stops. Game over. So, how do you get past a wall you can't break? Well, you'd all go through the wall, you get clever. You use software wizardry, and the playbook is just packed with these secret weapons. You've got techniques like Zero, which is this really smart way to get rid of any redundant copies of data floating around on your GPUs. There's something called flash attention, which completely rethinks a core AI calculation just to use way less memory. You can use more efficient data types. There's this special format called bfloat16 that's like a super efficient way to pack numbers to save space. And then there's my favorite, activation checkpointing. This is such a clever trick. To save memory, you literally just throw away some of that scratch paper. And then if you need it again later, you just recalculate it from scratch. Sounds crazy, but it works. So that brings us to our final section, the Nanotron advantage. Because look, we've talked about all these incredibly complex strategies for parallelism and for memory management, but the big question is, how does an actual human being use all this stuff? Well, that's exactly where a framework like Nanotron comes in. It's the thing that makes all this possible for developers who don't happen to have, a dozen PhDs in distributed computing. The whole point of Nanotron is to hide all that insane complexity. A developer can just write their AI model using the tools they already know and love, like PyTorch, which is one of the biggest open source frameworks out there. Then they basically just tell Nanotron, hey, I want to use this mix of parallelism strategies. And after that, they just hit go, and Nanotron takes over, handling all the fiendishly complicated work of splitting the model, managing all the communication, and actually running the training process. And this right here really shows you the difference it makes. I mean, before frameworks like this existed, trying to train a huge model was this completely custom, manual, and super error-prone process. You needed a whole team of hyper-specialized experts just to even attempt it. But with something like Nanotron, it becomes systematic, it becomes robust, and most importantly, it becomes way more accessible, which opens the door for so many more people to get involved in large-scale AI research. So after all that, what's the big takeaway? It's pretty simple, actually. This playbook, this is how it's done. This is how the AIs that are fundamentally changing our world are actually being built. The next time you hear about some mind-blowing new AI, just remember that behind all that magic is this incredible engineering, this combination of parallelism, memory tricks, and powerful frameworks that take a trillion-parameter model from a wild theory to a working reality. And that really leaves us with one last big question. We now have a solid playbook for training at the trillion-parameter scale, something that was considered completely impossible not that long ago. So what's next? What new, unforeseen challenges are we going to hit when we start aiming for 10 trillion parameters, or 100 trillion? And what in the world will an AI of that scale even be capable of?